In this video, I want to go through step 2 in a test hypothesis, and we're going to call this the test statistic. In step 1, we identified the null and the alternative that we were trying to test. And so I'm going to just over here, kind of off to the side, write a null and alternative that we may be interested in testing. And I'll go back to the one I think I was talking about in step 1. The null is the mean is equal to 100, and the alternative is the mean differs. So I'll say not equal to 100. All right, so we now want to collect some sample information, and hopefully it will help us to decide which of these two hypotheses we like. Remember, we've set it up. We'd like to say the alternative is true, but we're going to begin by assuming that the null is true. So we're going to go and take a sample. Now, because the sample is not in the entire population, it's going to be a subset of the population, there's a very good chance our sample information won't be exactly what the null says. For instance, our sample mean won't exactly be 100. And so the question becomes, what do we do with that? If our sample mean is 99.9, that's not a lot of evidence that the alternative is correct. If our sample mean is 3 or 3,000, well, that's pretty far away from the 100 that null hypothesis says the population mean is. That would make us want to lean a little bit more towards saying that the null is wrong and rejecting it. And so the question is, how the heck do you do that? And it's not an easy answer, but here's what I'll tell you. Assuming the null is true, the test statistic follows a known distribution. Now, typically in a Stat 1 class, the distributions we run into, and we've seen, are the Z and the T. In a Stat 2 class, you get introduced to a couple other distributions. And the specific distribution is sort of irrelevant for the conversation I want to have with you here. It's the fact that we know what to expect. And if you think about that statement, we know what to expect. If you know what the distribution should look like, you would be able to tell me what's expected or unexpected. And that's kind of the point. Well, if you assume the null is true, if you assume that the population mean is 100, now we can fall back on our sampling distribution work. We can fall back and say, well, if we take a large sample, then the sampling distribution of x bar will be, well, we'll know it'll be normal because of the central limit theorem, or approximately normal. The mean of the x bars is mu. The standard deviation is sigma over the square root of n. So we know what to expect. We know what should happen. If we're working with small samples, we've seen before that instead of working with the z distribution, if the population of x's that we're sampling from is approximately normal, we're going to work with the t distribution. And so either of those two cases, we know what should happen. And so I'm going to do this. For a lot of test statistics, and I got to be a little careful here in this video, and I guess I should probably broaden that and say these videos. The ideas we're going to talk about work. Some of the specifics don't always work. And when I say they're going to work, the general ideas that I'm expressing in these videos, the test statistic, the rejection region, the conclusion, the 4 videos that I'm going to make, apply to all tests of hypothesis. The challenge comes is as you go from one application to the next, some of the details change. For instance, I can't say that the Z distribution works for all tests of hypothesis. Likewise, I can't say, let me see where my pen's at right here. I can't say that this general form is going to work. However, that's what we're looking at now. That's the form of the test statistic that we're going to play around with now. And so specifically, if we're working with a population mean, it's going to look like this. And if you're looking at that, you should be thinking, we've seen this before. Yeah, we have. We've seen this pretty recently. And if you think about it, what did we say the value of the mean of the x bars is? I just said that that's equal to mu. And now you're left with a question, well, what's the value of mu? Well, look at the null hypothesis. If we believe the mean is, or if we believe, if we believe the null is true, what's the value of the mean in this case? We'd plug in 100. The value of x bar we get from our sample, the value of n we get from the sample, we're not going to know sigma, but we're going to estimate it with our sample standard deviation. The bottom line is, test statistics are going to be found on the computer output. These are going to be calculated for us. We're going to go ahead and tell the software, this is the test that we want to conduct. We want to compare to see whether the mean is equal to 100 or the mean differs from 100. And then it's going to go ahead and come up with a number. And now you're going to have to do something with that number. So the test statistic just takes all the sample information together, and I just see things like the sample mean, X bar, you got the standard deviation S, you got the sample size, and it takes all these numbers and kind of mashes them together, and we end up looking at a single number. And so the process that we're working through, the 4 steps, the first one is you identify, here's a test we want to conduct. If the null hypothesis is true, we should see, well, it depends. If we're working with large samples, we should see a Z distribution. If we're working with small samples, we should see a T distribution. At least with the context that I'm talking with the population mean. When you're talking about a population proportion, just like we saw before, we're going to end up, if we have a large sample, we're going to end up with a Z distribution. We can't work with small samples in proportions. We've talked about that before. We'll get there again. But there's a lot of similar information when we talk about confidence intervals and test hypothesis. What's a large sample? Well, I know a lot of you guys are probably throwing the word or the number 30 around right now, but what's a large sample? Well, the answer is it depends. It's going to depend on, are you working with means, in which case 30 or more is correct, or you're working with proportions. We saw before that n times p and n times q both have to be at least 15 for the sample to be considered large with proportions. It's going to be the same thing now. So we have some of the same questions. So we first, and this is always on you. I know a lot of times I show you computer output and it's like the null and the alternative are right there. Why do I need to worry about that? They're there because somebody asked for it. Somebody's got to identify what the alternative hypothesis is. Because when you go to the software, that's what you put in the software to say, show me the printout. And so identifying the test is always on you. And then you got to enter some data. Got to collect some data. You're going to get to do this on your projects for me. You're going to get to play around with the test hypothesis. You're going to tell the software, here's the test I want to conduct, and it's going to calculate a test statistic for you. So the first step, identify the test. That's always going to fall on your shoulders. The second step, the test statistic, well, the computer is going to do that based on the test you say that you wanted to conduct. The computer is going to come up with a test statistic number. And now your step, the next step, is to try to figure out how do you evaluate that number. And so step 3 is going to be evaluating the test statistic. And I know this is a short video, but I've never got a complaint that I've created a short video. So I'm going to end this here and we'll come back and talk about evaluating the test statistic. So long.